In this part we want to define what a rectangular dual is, and we want to explore a tool that we can use to get rectangular duals, which is the so-called regular edge labeling. Before we go to the rectangular duals, we want to make a very quick excursus to cartograms. In a cartogram, we are given a map and we have some data, and we want to transform all the, for example, countries in this map such that the area of them represents the data at hand. There are several different types of representations for that. For example, this so-called fisheye representation, where we just stretch everything in some way. We can have everything represented by disks or by schematized polygons. But very popular is also that we represent everything by rectangles, like here or here. For this, there exists a general framework. So we take our map as the input, and we compute the dual graph of it. So we place a vertex at every country, and we have an edge if they share a border. Now we first remove all the degree 1 and degree 2 vertices, and then we compute a rectangular dual for this, where we have additional vertices for the north, east, south, and west border. And afterwards, we can put back in the degree 1 and degree 2 vertices. Here we are also required to get a specific area for every rectangle. That one we will drop for now, but we will focus on this step, how to go from such a graph, where we don't have degree 1 or degree 2 vertices, to a rectangular dual. So let's define the rectangular dual. We have a rectangle, and we subdivide it into smaller rectangles. And then we place 4 rectangles on the outside for north, east, south, and west. This is a rectangular dual, so it's a partition of a rectangle into smaller rectangles with exactly 4 on the outside. Of course, this also represents a graph, namely this one here. So a rectangular dual of a graph is a contact representation with axis aligned rectangles, such that no 4 rectangles share a point, because otherwise we would have a crossing here in the underlying embedding, and we only want to do planar graphs. And the union of all rectangles, again, is a rectangle. There's a theorem by Kozminski and Kinnan from 1985 that says that a graph has a rectangular dual if and only if it is a PTP graph. What is that? That's a properly triangulated planar graph. So what does this mean? Planar, of course, means that we don't have any crossings. So we have an embedding where no crossing exists. Triangulated, we also already know, that means that every face is a triangle. But in properly triangulated, this only corresponds to the interior faces. All the interior faces are triangles, and the outer face is a quadrilateral. Here we have 4 vertices. But properly also means that we have no separating triangle. A separating triangle is a triangle where we have some vertices on the outside and some in the interior. So here it's only important that we have nothing inside the triangle. Because if we look at some representation of this, we have a rectangle here for the top vertex. Now we need one that is placed here, and the next one must touch both these rectangles, so we have to place it here. And now everything that's inside has to be placed here at this point, and that's not possible. There's no space to place all the rectangles that have to be inside here. And these are the only conditions that we need. Planar, interior face is triangle, outside face quadrilateral, no separating triangle. If we have this, then we can get a rectangular dual, and if any of these properties do not hold, then there is no rectangular dual. From a rectangular dual, we can read off a so-called regular edge labeling that will be very important for us to later reconstruct the rectangular dual from a graph. So let's have a look at 2 rectangles here. These 2 rectangles touch with a horizontal segment. But of course this is not the only rectangular dual. We can just locally transform this a little bit so that they touch with a vertical segment. Now we want to combinatorically describe those type of contacts. So there are 4 types. We can have a horizontal, where green is above orange or orange is above green, and we can have vertical, where green is to the left of orange or where orange is to the left of green. So there are 4 types of edges that we basically can have. And that we encode with a color and a direction. To get a regular edge labeling from the rectangular dual, we will just draw all these segments blue if they are horizontal and red if they are vertical. And now every edge that intersects a red segment is colored red, and every edge that intersects a blue segment is colored blue. Also, all the edges are directed from left to right for the red edges and from bottom to top for the blue ones. And this is our regular edge labeling. This describes exactly for every pair of rectangles how their contact works out. If we look at a single rectangle here, and we look at the order of the edges around this rectangle, and it's clear that we must have in this order outgoing blue, then outgoing red, then incoming blue, then incoming red. This is quite similar to the bimodal property that we had in upward planar drawings. There we only had one color and we must have only outgoing, then only incoming. Now we have 4 types of edges, so this is also called a 4-modal vertex. Also, if we look at the exterior vertices, here we can see this is at the top. All the edges come in. So at the north vertex, we can only have incoming blue edges, the east only incoming red, here only outgoing blue, and here only outgoing red. So these are necessary conditions we must have for a labeling to be a regular edge labeling. And Kant and He in 1994 gave a linear time algorithm that takes as the input a properly triangulated planar graph, then calculates for that a regular edge labeling, and from that regular edge labeling calculates a rectangular dual. And that's the algorithm we want to focus at in this lecture.